What I want to talk about today is the computations that we astrophysicists do when we calculate large-scale structure and also galaxies. So first of all, by way of orientation, probably everybody knows this. So the Earth is 8 light minutes from the Sun. Jupiter's 40, Saturn's 80. It takes light less than a day to cross the entire solar system. It takes like 25,000 years to get from the center of the galaxy out to where we are, about halfway out from the center to the edge of the visible galaxy. The galaxy is about 100,000 light years across. Our galaxy, in turn, is just one of about 10,000 galaxies in what we call the local supercluster. 10,000 big galaxies like the Milky Way. In the local supercluster. The local supercluster is more or less centered on the Virgo cluster, the densest concentration of galaxies anywhere around us. So what I want to do to give you a sense of what galaxies look like and what the distribution of galaxies is like is visualize a trip starting nearby the Earth and the Milky Way, and then going across the Virgo cluster, taking a slightly circuitous route, going across the supercluster to the Virgo cluster. We're going to start, actually, would it be possible to close the back doors?
Yeah.
Because I'm going to be showing a lot of these videos, and the videos are very dark, because, you know, it's the night sky. Thank you. Good. Okay, this is looking better. So we're going to start heading toward this familiar constellation. Not so easily visible this time of year. So what constellation is this? Exactly. And this is the Milky Way. We're going to head directly for this thing. This is the belt, that's the sword, and this is the Orion Nebula. So there's about 100,000 stars whose distances we know pretty accurately from the Hipparcos satellite. And those were put in the computer along with these astronomical images. There's this little dark cloud with the shape of a horse's head. When we pass the Horsehead Nebula, we're about 1,500 light years from home. Here's another one of these stellar nurseries, like the Orion Nebula, where a lot of young stars have formed. And the O stars, the brightest of all the stars, light up the nebula and push away gas and dust. Here's another one of these nebulae. Nebula just is Latin for cloud. So this one is the crab. You can see the crab pulsar flashing in the center. So that's the debris from a supernova explosion that we saw on Earth about 1,000 years ago. Explosions like this make a lot of dust, which blocks our view in the disk of the Milky Way. So let's rise up and out of the disk to see the magnificent panorama of a giant spiral galaxy. As the galaxy recedes into the distance with the large and small Magellanic Cloud, everything we see now is a galaxy. The Andromeda galaxy is coming into view, the other big galaxy in the local group, and in the foreground, the triangular M33, the other spiral galaxy, the third spiral galaxy in the local group. As we pass through this giant gas cloud in M33, we're now 2 million light years from home. Now we're heading for the Virgo cluster, just coming into view over here. But we're going to take a view past some of the prettiest nearby galaxies. That was M81 and M82 we just passed. This is the whirlpool, M51. Now, you'll notice that there's this chain of galaxies. that leads into the Virgo cluster. We're going to jump into the chain about here, and then we're going to ride down this filament of galaxies toward the Virgo cluster. We're now entering the filament. We're approaching the Virgo cluster. We've been seeing mostly spiral galaxies, but now we're starting to see elliptical galaxies, big balls of stars without any disk. This trip ends at M87, the giant elliptical in the Virgo cluster. It has a gigantic black hole in the center with this jet coming out of it. The mass of this black hole is about 5 or 6 times 10 to the 9. 5 or 6 billion times the mass of our sun. So, now what I want to talk about is how we simulate these things. So astronomical observations represent snapshots of moments in time. It's the role of astrophysical theory to produce movies, both metaphorical and actual, that link these snapshots together into a coherent physical theory. And I'm going to talk about 2 different kinds of simulations. Cosmological dark matter simulations without any baryons, just dark matter and dark energy. And I'm always going to assume dark energy is just a cosmological constant. Please keep the door closed. As I explained earlier, it will make it very hard to see.
People can't see the room, so why don't you close the door and watch the simulation? Is that okay?
All right, sure. Except I'm going to be showing simulations continuously.
I'll stand up here.
Okay. So the dark matter simulations take into account the dark matter, including the ordinary matter, which we're just treating as dark matter for the time being, and the cosmological constant. And they show large-scale structure, the growth of structure, and dark matter halo properties. So the drawing on the stoop says quarks, neutrinos, mesons, all those damn particles you can't see. That's what drove me to drink. But now I can see them. And you too will see the dark matter because I'm just about to show a bunch of simulations starting right now. And so all the simulations are just going to show dark matter. What's bright is not stars or light, it's just dark matter. So now, several of the lectures by Matt in particular talked about co-moving coordinates. And so what I'm going to do for most of these is I'm going to show things in co-moving coordinates. If we showed the way structure evolves, small to larger to today, you wouldn't be able to see what was going on until it got to be pretty full size. So one way of thinking about what co-moving coordinates are is we just take out the expansion. We blow everything up, in other words, to its current size. Got the idea? Those are the x coordinates. There's the a squared times dx squared. So the a is the scale factor. If we show things in the x coordinates, that's co-moving coordinates. But maybe this is a more graphical way of understanding what co-moving coordinates are. Please close the door. So what this is a simulation of the local region of the universe. It's called the Constrained Local Universe Simulation, Cruz. And what you can see is how matter flows along the filaments. This is a region that's about 250 million light years across. So much bigger than the local supercluster. Okay, the simulation is now over. And now what we're doing is simply taking a trip on a straight line through the simulation so that you can admire the filamentary structures. In a little while we're going to pass the Milky Way and Andromeda and you'll see the Virgo cluster. The Milky Way is going to be a little blob about that big. And Andromeda is going to be right nearby. The Virgo cluster isn't going to be nearly as big as this. This is a giant cluster. It's going to be more like this one. Okay, we're just passing the Milky Way. Now I really should show you what I was talking about when I said we were just passing the Milky Way. So there is the Milky Way, that little dot down there. This upper dot up here is M31, Andromeda, and this little dot over here is just an interloper. It's a foreground or background thing. This is the nearest cluster of galaxies. It's pretty small, called the Fornax cluster. And here's the Virgo cluster up here, which is part of one of these chains. And this is that filament of galaxies that we jumped into that lead to the Virgo cluster. So now I'm just going to show you the end of that video, just showing you the Milky Way and Andromeda and Virgo, so you can follow it. So there's the Milky Way, there's Andromeda, there's Virgo. Milky Way, Andromeda, Virgo's already left. So we're just a little piece of a great big universe. Okay, now this is the evolution now in real space, showing the expansion of a halo that could make a galaxy. The galaxy is going to form right in the center. Notice it was expanding, but it stopped expanding. Now this material is falling in. This is flying away though. Notice how the dark matter subhalos just go right through. Clouds don't do that. Notice all the substructure. So to recapitulate, expanding, expanding, expanding. Halfway to the present, the universe is now a little over 14 billion years old. This region has stopped expanding, and this region is now flying away from it, never to return. But other stuff is still falling into this region. This is today, and you sometimes hear about outer space, which just means beyond the Earth's atmosphere. That's not a particularly useful distinction. The really important distinction is between the space that's contained by gravity and the space that is expanding faster and faster and faster because of the dark energy. So this region is held together by gravity. It's tame space. This is not. This flew away and will never come back, and it's flying away faster and faster, so that's wild space. Here's a sort of blow-up of a halo like this. This is from a series of simulations that was called the Aquarius series, led by Bolshoy. And so this whole thing is the dark matter halo of a galaxy like the Milky Way. And this is the size of a galaxy like the Milky Way, that 100,000 light years. So the volume is 10 times larger, a little more than 10 times larger than the visible galaxy in one dimension. But of course it's three-dimensional, so that means the volume is more than 1,000 times the volume of the visible galaxy. This is what galaxies really are. Incidentally, there's this huge amount of substructure. Only a small fraction of these are satellite galaxies. And one of the issues that people raise is, isn't this a problem? Shouldn't there be a whole lot more satellite galaxies? And actually, the harder we look, the more satellite galaxies we find. So I think the general view is that that's not a big problem. We also understand how hard it is to make stars in these very small dark matter halos. So that was once regarded as a fairly serious problem, but it seems to be evaporating. So how does this fit into the cosmic web, this large-scale structure of filaments and so forth? More or less like this. This is the best simulation currently available of the large-scale structure of the universe. My colleague Anatoly Klipin was born in Moscow, and when we had to choose a name for it, he suggested Bolshoy. And we all knew what that meant. We knew enough Russian. And so we thought that was a great idea. So to a Russian, Bolshoy doesn't just mean big, which is the sort of literal translation. It's big in the sense of great, grand, marvelous, grown up. So here's this amazing simulation, which was run on NASA's biggest supercomputer. It took a lot of supercomputer time. And to give you a sense of what a simulation like this entails, let's look at a little region that's only 1,000th the size of the simulation. So 100 million light years on each side. So that is centered on one of those big clusters, more precisely the dark matter halo of a big cluster. And you see how the clusters form where the filaments intersect, and how the galaxies form mostly along these filaments, with large regions empty. So what we're doing is rotating it to give you the three-dimensionality and zooming in so you get a better sense of how the simulation works. Remember, this is only 1,000th of one of these big simulations. When we run the simulations, we store many, many time steps. For this one, we stored 90 time steps. And we identify every halo and every time step. And then we can use that to simulate the evolution of galaxies and clusters. So let's see how just this big halo formed. Not the whole thing. We actually do the same calculation for every single halo. But I just want to show you the calculation of how this particular halo formed. So what I'm going to do is show you every single little dark matter halo, blob of dark matter held together by gravity, that formed and merged and ultimately became this object. Again, realize we've done this for every single dark matter halo in the entire volume. Every one of these is going to be part of that big halo. Every one of these is going to host a galaxy. Notice how they're flowing in along this dimension and then also that dimension. And to some extent this way. So this is called the merger tree. And there's an art to constructing these things. There's been a lot of work that's gone into this, especially by a former graduate student, now a postdoc at Stanford, who's about to move to Space Telescope Science Institute, Peter Cruz. So we're keeping track of the redshift and the age, and it's just about today, and there we are. That halo is now formed. The Icelandic folks in your love that previous video, that rotating thing. You can open the door now, because I'm not going to show another video for 2 minutes. So she asked for a copy. It was shown on the National Geographic TV special, in which I also gave a tour of NASA Ames Supercomputer Center. And she asked for our video. Of course, we were delighted to give it to her. And she's doing a tour, I think she's still doing it, in which she has a cut called Dark Matter, which has nothing to do with dark matter. But anyway, she shows this in the background, which of course delights us. And I wrote a popular article about this with Trudy Bell, which was the cover article in the July 2012, so last year, July issue of Stein Telescope magazine. And it's online, if anybody's interested. So it's sort of popular account of how we do these simulations. I also wrote a somewhat more technical article for IEEE Spectrum, the magazine of the computer people. So this shows some snapshots of how the simulation evolved. For that visualization that I showed of the evolution of the Cruz simulation, the local universe simulation, we stored 7,200 snapshots so that we could do a 3-minute video at large scale. And that was the opening show for the Adler Planetarium's new Sky Theater, which has 8,000 pixels across, and I wanted to do something that was sufficiently special. So we did that. We've only stored 90 time steps of this, though. So it's not enough to do a smooth animation. Now, the two key parameters, there's 6 important parameters and then a few other parameters for cosmology. But the most important ones for these simulations are omega matter, realizing that omega lambda is about 1 minus omega matter, exactly 1 minus omega matter if the universe is flat. And sigma 8, which is basically Q in the notation that Anthony used, So this is the amplitude of the power spectrum, the A that multiplies the K to the 1 minus n. And this is the amount of matter. And so we had available WMAP5 and WMAP7 when we did Bolshoy, and we also had various other data from clustered observations. And we chose these parameters for the Bolshoy simulation. Omega matter of 0.27, omega sigma 8 of 0.82. And then along came Planck, March 21st of this year, with these incredibly small error bars. And we decided that Bolshoy is now 4 of these little error bars away, primarily in the omega matter direction. So we really had to rerun it. So it's running right now on NASA's biggest machine. It'll be done in about a week. It's taking millions of CPU hours. I don't know quite how many yet. It's using up a good part of my allocation this year. But we figured there was no choice. We had to do it. And now we're storing 180 time steps, and as of yesterday, we'd stored 142. Notice the Millennium simulation, which was the first of these big simulations at reasonably high resolution, is now more than 8 sigma away in this direction and in that direction. It's hopelessly bad. Also, the analysis that we've done on Bolshoy is far better than what our European competitors did on Millennium. Although, of course, now they know all our secrets, so they can do a better job if they want to. So, my European colleagues have also rerun big simulations with hundreds of billions of particles, but with much lower resolution, basically the whole visible universe, with exactly the same Planck parameters. So those will all be made public very soon. So this is the Bolshoy Planck cosmological simulation. And of course it's going to look similar, but it's actually interestingly different. So for example, at redshift 3, there's 5 times as many of the most massive galaxies than in the original Bolshoy simulation. That extra omega matter really makes a big difference. More growth at early times and longer matter domination. So how do we test these things? We've got to do the test by a statistical method. And what we find is, so these are called pi diagrams. So we look out in a certain thin stripe across the sky of constant declination. And so these are outer angle. And so this is the real sky, and of course we see fewer and fewer galaxies. We get, in the Sloan digital sky survey, they get every galaxy brighter than a certain brightness. And of course, as you go further away, that's only the brightest galaxies. Now, we can basically do the same kind of thing, filling the dark matter halos with galaxies by a fairly standard procedure. If you want to ask me, I can explain what the procedure is. But the procedure does give the correct properties of the galaxy. So for example, we can calculate the correlation functions of the galaxies that we get this way, and they're identical to the correlation functions that we get here. But we can do lots of other tests. So I wanted to give you an example of the kind of test that we've done. So this is the real sky. Incidentally, that's Connie Rakasi, one of my colleagues here at the UC Santa Cruz astronomy department. And she is the head of the second part of the Sloan Digital Sky Survey. So one of the interesting questions is, how likely is it that you've got a galaxy the mass of the Milky Way that has 2 big, bright satellite galaxies like the large and small Magellanic Cloud? If you're in the southern hemisphere on a dark night, you can't miss these things. They're really bright. The Milky Way goes right across the middle of the sky in the southern hemisphere at the right time of year, and you can't miss these things. But we call them the clouds of Magellan because, Magellan and his crewmates on their trip around the world saw these things. But of course, the people who lived in the southern hemisphere were quite familiar with it. In any case, how often do these things exist? Well, we can ask that question of our simulations because the Bolshoy simulation will see every object as big as this, as well as every object as big as this. And we have like 100,000 of these or more in the simulation. So we're going to have lots of statistics. And then we can also ask the Sloan Digital Sky Survey, which is a map of the sky, the part of the sky they've surveyed. And it turns out that there's about 3,000 Milky Way analogs in the Sloan Digital Sky Survey that have been surveyed deeply enough that we would see objects as bright as these. And so here's the calculation. How common is this? The simulation plus this way that we fill the dark matter halos with galaxies predict the likelihood of 0, 1, 2, 3 large satellites as bright as these. So that's the real sky. We just look at lots and lots of Milky Way analogs and we count the number of times that we get 1 or 2 or no, 1, 2 big satellites. And we do the same thing in the simulation. And as you see, the numbers are coming out looking pretty similar. Here's the statistical summary. So the red, this is the number of times, the frequentist probability, that we get no satellites. And this is the number of times we get one satellite. So it's like about 15% one satellite, about 60-some%. No satellites as bright as the large and small Magellan Cloud. About 8%, 7% that we get 2 satellites. 3 satellites, that's about 1.5%, and so on. And of course, the error bars get bigger and bigger as you go to more and more satellites because the number of cases is really small in this 3,000 analogs of the Milky Way in that part of the sky that's been surveyed deeply enough so far that we actually see those satellites. But every one of these is within the 1 sigma error bars. So every case agrees within the observational errors. And this is a general fact about the large-scale structure of the universe. In many cases, we've made predictions long before the evidence was available. In this case, the evidence was there, but we didn't know it when we made the prediction. The observers did the calculation of these actual numbers independently of our calculation of the red points. And there's no cases where there's a discrepancy. Lambda CDM just seems to be right. You've seen that in great abundance now with the power spectrum of the cosmic microwave background fluctuations. But what I'm trying to show you here is examples of how we know that it's also true with the galaxy distribution. Now, at the end of his talk, Anthony mentioned semi-analytic models, which is a more sophisticated way of filling all the dark matter halos with galaxies. And we've now done that. And there's a series of papers that are going to come out. So my group here at Santa Cruz has 3 papers, and then we are working with my former grad student Risa Wexler and her group at Stanford, and also Darren Croton, who did the Millennium Simulation semi-analytic model. And they've all been given access to Bolshoy. In fact, Bolshoy is publicly available. And so based on the same halo merger tree, 3 different groups have now done semi-analytic models. Now the basic way we do semi-analytic models is summarized in this diagram. So every halo forms a galaxy. And the galaxy initially forms as a disky thing. Gas cools and falls onto the disk and turns into stars. And if this dark matter halo falls into this guy's dark matter halo at a later time, here it is inside, and there are physical processes that will make it merge out to the center. There's a process called dynamical friction, for example, which is a purely gravitational process, but it's dissipative. And the result is that dark matter gets a little bit of extra energy, this thing loses energy, and it falls onto the center. And then that can produce a lot of new stars. And it can also light up the giant black hole that's often lurking at the centers of these things, and produce a quasar. And it'll heat up the gas. And the process seems to prevent further formation of stars. And so you get, at the center, some old galaxy with no new star formation. And the stellar population becomes redder as the new stars stop forming. The young stars, those O stars that lit up those little nebulae, they only live a few million years, then they supernova. And the B stars, well, they live tens of millions of years, and they don't supernova, but after those stars are gone, the rest of the stars are yellower or redder, and so that's all that's left. So the gas is heated, it collapses to form gravitationally bound structures, You make stars, you follow all the physics, the cooled gas collapses form a rotationally supported disk, the stars form, massive stars reheat and can even expel some of the material. Mergers trigger bursts of star formation. AGN, active-galactic nuclei, that's the general name for what happens with the black holes at the center, cuts off star formation. Including the effects of dissipation in gas-rich galaxy mergers leads to the observed elliptical size-mass relation. So it's known elliptical galaxies of a certain mass have a characteristic size. That comes out of our new work. Including spheroid formation by distance abilities, reproduces the numbers of galaxies of all types, both today and at earlier times. So what we do when we run these models is we're using all this data that was stored from the merger tree, and then we basically sphericalize everything. We treat all of these galaxies with simple spherical cows. And you know about a spherical cow? Somebody was asked, so how many shoes can you make from a cowhide? And the answer is, consider a spherical cow. And a spherical shoe for that matter. So all you want to do is calculate the relative areas for a first approximation. So this is a spherical cow type theory. Because what we're going to do is we're going to follow 1 million galaxies at a time. One that tries the whole evolution of the galaxy population. So we don't have the computer time to do each one in detail. Later on I'll tell you about how we do them in detail. But anyway, there's a big program to do this sort of thing, and the different groups sort of compare results, and we're starting to converge now, and to get results that look pretty consistent with the universe. Elliptical galaxies follow a size-mass relation, as I said, and the semiautomatic model correctly predicts this and the other known relations of elliptical galaxies. So these are 4 examples of elliptical galaxies. And this galaxies follow a relation between the speed that they spin and also their luminosity. The luminosity and the mass go as the 4th power, roughly, of the rotation speed. That's called the Tully-Fisher relation. And the theory correctly predicts this. And finally, the theory correctly predicts the numbers of these different kinds of galaxies, the disk galaxies and the elliptical galaxies, at all different masses. And it predicts a lot of the intrinsic properties. So you know, we're not doing badly. But we really want to understand the details of how galaxies form. And to do that, we do what's called hydrodynamic galaxy formation simulations, which means that we're following the gas. We now are doing them in full 3-dimensionality, and the size of the halo, remember, is about 1 million light years across. The size of the visible galaxy is about 100,000 light years across, and our simulations have a resolution of better than 100 light years. Now that may not sound like very good. I mean, the distance from us to the nearest star is about 4 light years. But it's currently more or less the state of the art. Because if you're doing 100 light years, and your thing is 1 million light years across, that's a factor of 10 to the 5th in length. But that means that the number of regions you have to simulate is 10 to the 5th cubed at high resolution, 10 to the 15. And that's pretty much the limit of what you can do with modern supercomputers, even using every trick in the book. As computers get better, we will do better. And at the end of the lecture, I'm going to tell you about what we think is the future evolution of computing. But anyway, the purpose of these is to study the evolution of galaxies, formation of galactic spheroids via mergers, galactic images in all wavebands compared to observations, including stellar evolution and the effects of dust. So this is now a blow-up of this motion along filaments into a forming galaxy, which is right in the very center. That's where the galaxy is forming. Now, these blobs of gas are also little galaxies that will feed into this central region where a bigger galaxy is forming. So that's how the flow goes. And you saw how matter flows along the filaments in that Cruz simulation that I showed you. So this is now doing a much higher resolution simulation where we zoom in and actually show the way it works. Okay, could you close the door? Because I'm going to show a bunch of simulations again. So this is an example of a hydro simulation. The white is actually stars, simulated stars. And the blue and yellow and so forth is gas, and the redder, the higher the density. And notice how you get this spiral galaxy going, and even though it gets bombarded by lots of stuff, it keeps rotating and rotating and rotating, and it's got a fairly thin disk, and that's how these simulations work. That's pretty typical. So here again, another visualization. So this is actually the same kind of simulation. What we actually do when we do these simulations is we simulate a large volume, about 40 megaparsecs across. A megaparsec is a little over 3 million light years. So this is about 120 million light years across. But the region that we use high resolution in is just this little tiny region in the center. 2 megaparsecs, about 6.5 million light years across. And remember, a big galaxy is only 100,000 light years across the visible part. So this is still a lot bigger than a galaxy. It's basically everything that could possibly affect this galaxy directly. And we do this larger region because we also want to get the tidal forces, the gravitational forces, from a fairly large region. So now what I'm going to do is I'm just going to zoom in on this little region. Remember, all the high-res stuff is here. So you see, we don't just form one galaxy, we form lots of stuff. Lots of little dwarf galaxies along every filament. Galaxies are forming. We've run about 100 of these simulations, a little over 90. And so that gives us a huge amount of data. And of course, we store the data at many time steps. This was just showing you one time step and several of those little galaxies that were forming. So then what do we do with it? What we want to do is compare it to the observations that we're getting from Hubble Space Telescope and other telescopes at various wavelengths. And that means that we have to take these simulations and convert them into images that have all the physics of the real images. So one of my former students, Patrick Janssen, created a code with me called the Sunrise Code, which is now the world standard. Everybody basically uses this code. And what it does is it makes realistic images. So as the simulation goes, millions of star particles form. Each star particle could represent hundreds of thousands or so stars. And so we keep track of when every group of stars form. And the star particles start out very blue, ultraviolet, because they've got those O stars and the B stars. And then as those stars die out, the colors change, the wavelengths emitted change, and we follow all of that. The computer's basically just doing the bookkeeping. And we also have to take into account the effect of the dust, because you saw that galaxies like the Milky Way have this dust in the disks, and that actually absorbs a lot of the light. And of course, the energy is emitted, but it gets emitted typically at longer wavelengths. And so what we have to do is include the scattering of the light by the dust, and the absorption of the light by the dust, and then the re-emission by the dust at longer wavelengths. And so we have to calculate what the temperature of the dust is throughout the whole volume. And we do all of that. And we use what's called the Monte Carlo method. We follow millions of rays that shoot out from all the star particles and scatter, and we ultimately care about the ones that make it into our cameras. So we surround the thing with cameras, of course, computed cameras. We can follow hundreds of wavelengths simultaneously. We carry the wavelengths as a vector in the calculation. And graphic processor units, these gadgets that are as fast as a Cray computer of 10 years ago, which cost $30 million, and they only cost a few $1,000s. And so we're allowed to use a system at NASA Ames where they've got 64 of these graphic processor units, each one with a bunch of computational cores. And our group is the only one that's been able to use very much of this time because we wrote the first code that can actually efficiently use this. So, you know, constantly have to keep changing things to keep up with the evolving technology. So there's a face-on and an edge-on spiral galaxy calculated by this code. Looks very realistic. And this is the wavelengths. This is ultraviolet, visible light, infrared, far infrared, This is called sub-millimeter, that's a millimeter, 10 to the minus 3 meters. And the blue is what it would look like without any dust, face on. The green shows that a lot of this ultraviolet is getting absorbed. And edge on, essentially all the blue and ultraviolet light is absorbed, and even a lot of the visible light. And this light then gets re-emitted at these long wavelengths. That's 100 microns wavelength. Visible light is in there at a fraction of a micron. Micron is 10 to the minus 6 meters. So we do these calculations for every one of our stored time steps of galaxies. This shows a visualization of a merger between two big spiral galaxies. So to make this, we had to run this program about 20,000 times, because every time step, there's 30 frames per second. We had to run this. The two galaxies go past each other. When they sideswipe each other, their gravity causes the formation of a lot of new stars and new structures. The galaxies are now coming back together, and now the centers will merge very quickly. This music, incidentally, and much of the other music is by my wife, Nancy Ames, who's, among other things, a composer. And what happens when two big spirals merge is that you make an elliptical galaxy. The stars that were in those thin disks go every which way. So this whole process that I'm showing you here takes about 2 billion years. About 1 billion years for the merger, and then another 1 billion years to convert it into an elliptical galaxy. Now we're just rotating it around. There's that dust lane. You may have remembered that some elliptical galaxies have dust lanes like that. I showed you an example when I showed you those 4 ellipticals. So, incidentally, that's what's going to happen to our galaxy plus the Andromeda galaxy in about 5 billion years. It's going to turn into an elliptical galaxy, which we can call Milky Andromeda, or Milkomeda. And around that same time, the sun is going to turn into a red giant and swallow the inner planets, including Earth. The white dwarf that will result is almost certain to be ejected into a great distance, but not totally from the galaxy, from this forming elliptical galaxy. And so it's going to spend most of its time far out. And then occasionally it's going to whiz in close to the center and come flying back out again on an elliptical orbit. So what this is a blow-up of one of these regions where a galaxy is forming. And so this is a face-on view and an edge-on view. And this is gas. But now let's convert this into what it would look like using the sunrise code. And also let's degrade the resolution so that it's at a redshift of 2, which corresponds to about 10 billion years ago, when galaxies like the Milky Way were just starting to form. So, this thing actually looks like a spiral galaxy. And if you look at it edge on, it looks like this. Well, these are observed galaxies at redshift 2. And of course, I didn't just pick any old observed galaxy. I picked ones that look sort of like these. Now, to do this properly, you have to do a statistical study. You have to look at thousands of galaxies, thousands of simulated ones, thousands of real ones, and we've done that. We've subjected 36,000 galaxy images to detailed analysis, both by computer and also by observers. We have a team of 50 astronomers, including grad students. And they look at 200 images a week, week in, week out. And so these 36,000 images have been looked at by a minimum of 3 and an average of 5 different astronomers. And we've also subjected thousands of our simulated galaxies to the same test. And we've now compared the simulations to the observations in a systematic way. The papers are about to be submitted. And the simulations don't look bad. The fraction of clumpy galaxies like this in the observations and the simulations is about 50% at redshift of 2. So, you know, we're not doing too badly, but we do know that there are problems that still haven't been resolved with the simulations. Now, this is the effect of dust. This is without dust down here, a face-on and edge-on view. When you include the dust, it dims the light, but it also spreads it out a lot because the dust scatters the light. So what I'm going to do is show you the effects with the dust. So this is the evolution of one of these simulations. Notice how, and I'm just showing you some time steps. Notice how constantly things are bombarding these galaxies. The reason that galaxies at high redshift look so irregular is that they're constantly being bombarded. At redshift 4, every dimension of space is 1/5 what it is today, redshift plus 1. And so that means that the volume is 1/5 times 1/5 times 1/5, 125th smaller. And the number of galaxies is larger because a lot of the galaxies have merged after that. So it's a bumper car era. And you see how some of these are very clumpy. And as I say, we've now done a statistical analysis, and it looks like the simulations are in the right ballpark. This is work by one of my current graduate students, Chris Moody. So one of the things that's made this, you can open the door now, one of the things that's made this really very fruitful is the astronauts, in their last visit to the Hubble Space Telescope in 2009, installed a new camera that uses military technology to give us these beautiful Hubble-type images that are perfectly sharp, edge to edge, but now into the infrared. And this shows you what we can do with the new camera, the Wide Field Camera 3, compared to our best previous camera, which was the Advanced Camera for Surveys, ACS. These are the same galaxies. But see, here we're looking at these galaxies at redshift 2, 10 billion years ago, as they would appear in visible light. So the old stars are showing. This is showing only ultraviolet, which is all we can see when we use this device, which only sees visible light today. But what was ultraviolet at redshift 2, the wavelength increases by a factor of redshift plus 1, 3. So all we can see today is what started out as ultraviolet light, very short wavelength light. So, of course, we get both. We get a bunch of ultraviolet, and then we get a bunch of visible. Bunch of different wavelengths. So that really gives us a much better insight into what's going on with these galaxies. After the astronauts repaired Hubble and installed new instruments, there was a huge competition to basically dominate the time on Hubble Space Telescope. And our team won. And that's called the Campbell Survey. And the head of that is Sandra Faber, who's also the director of University of California Observatories, which is headquartered here at Santa Cruz. So this is the largest project in the history of Hubble Space Telescope. And this is the Campbell's website, campbell.ucla.org. So just to give you some explicit data, so here's a simulated galaxy face-on and edge-on. And this is what it would look like close up if you could see it back at redshift 2, 10 billion years ago. But we can't. We see it as Hubble Space Telescope sees it. In about 6 years, if all goes well, James Webb Space Telescope, a much bigger telescope with much better infrared capabilities, will be up there, and we'll be able to get somewhat better images. But this is what we've got to work with for the present. So this is rest frame visible, this is rest frame ultraviolet, and this is what it would look like if you could see it close up. So, you know, you certainly see that there's this thing and there's that thing, and can you see all these little blobs? Well, not all that well. But this is what we got to work with, because this is what the real images also look like. And there it is edge on, and that's what it looks like edge on. So it's kind of tough. Incidentally, you can combine these images to make what they call a color composite image, which is what we've done here. And you know, it looks kind of ratty, but that's what we're giving to Galaxy Zoo. More about Galaxy Zoo in a little while. So this is what these images would look like if we hadn't taken the effect of dust into account. the blobs would be a lot brighter. Incidentally, astronomers often use the negatives, if you like. So what's dark is actually bright. And see, in fact, it should all be black except for, so you understand that we've switched. And we're showing you the negative image. But anyway, if you don't include the dust, these blobs are much, much brighter than they are in reality. The brighter the blob, the more dust is forming, the more dust is absorbing light, and so you get objects that look much more like a real galaxy. So these are real images, and these are the simulated images. Simulated, real, simulated, real. Just for example. So now we're systematically comparing the simulated and observed images. One of the problems that has plagued galaxy simulations is that you want to make simulations that look like this, but until recently, simulations tended to make objects that had almost all their stars with low angular momentum. This is the angular momentum in units of what's required to have a rotation-supported disk. And you see that there's just a very little bit of disk and mostly a great big bulge. And that doesn't look like the real universe. So this was a paper just published last year where most of the teams in the world tried their best to do the best simulation they could. And not one of these looked like a real galaxy. But here at Santa Cruz, Javier Agudas, the Chilean graduate student, who now is going to be, she was a postdoc in Zurich, and her new postdoc starting this fall is at Princeton. So that's Javier Agudas. Her advisor was Pierre McDowell, my colleague here in the Santa Cruz Astronomy Department. And they produced a spiral galaxy that looks just like the Milky Way. It has lots and lots of stars that are rotating in a disk, just like a real spiral galaxy. And the trick was that it was the first high-resolution simulation that included some of the relevant physics. So high resolution is essential. If you don't have enough resolution, you're just going to mess up. Inspired by this, my colleagues and I, Piero and I, and leading people in other institutions, formed a project that, after a naming process where everybody suggested names and then we voted on it, it's called Assembling Galaxies that Resolve Anatomy, the Agora project. This was actually suggested by Javier Agudas, this name, and she says, "Oh, I know, the Greek has an accent over the final alpha. It's Agora." So I'm trying to remember to pronounce it Agora. These guys were all here at Santa Cruz, together with a lot of other people, last August to initiate this project. We now have more than 90 astrophysicists using 9 different codes that have joined together. We have generated initial conditions for objects that at redshift 0 today will have 10 to the 10 solar masses, 10 to the 11, 10 to the 12, and 10 to the 13. So we'll make massive galaxies and little dwarf galaxies and Milky Ways and very typical smaller galaxies, and both many mergers in their merger tree and few mergers. And these are initial conditions that can be used with every available code. So the idea is that people are going to simulate with all the different codes exactly the same initial conditions, and we're going to use the same basic physics. So the only difference is going to be the exact way that things get implemented in the codes. And then we're going to compare all the results at many different time steps using the same tools. A visualization analysis package called YT, written by Matt Turk when he was a graduate student at Stanford, and now he's a postdoc at Columbia. And all of the outputs are going to become publicly available, and all of the images and spectral energy distributions for all the time steps can go into Sunrise, and we can make images that can be compared by us and others with the observed galaxies. This project is called the Agora Simulations Project. If you just Google Agora Simulations, it comes right up, or you can look at our website. We have 4 working groups that have generated initial conditions and the codes. And we have 10 working groups that are analyzing outputs. And we're starting to get outputs from the simulations already. And there's going to be another big meeting here at Santa Cruz next month. So our kickoff meeting was last August. The meeting is going to be this August. And there's various other things happening this summer. And we've had various other meetings here. So I've shown you a bunch of different visualizations. Milky Way meets Andromeda, our galactic future, the Bolshoy simulation. Do observations agree with the distribution of galaxies they seem to? Do we live in some special environment, Milky Way's own region? The merger tree. Do various galaxies fit in halos like the right numbers of spiral satellite galaxies? And I've also tried to use different methods of showing you the three-dimensionality. The simulations are four-dimensional. They have 3 dimensions of space and they change in time. So here we used extreme perspective. Here we used rotation. Here, we're using co-moving evolution. And then we did a fly-through. So these are all different methods of visualizing the results. And they're all interesting and useful. But they're not really good enough, because what we'd really like to do is really see all the three-dimensionality all the time. So to do that, we can use 3D, the kind that's projected on screens. Incidentally, we also work with the big planetariums. Adler in Chicago is the biggest in the United States, and it has this dome show that can do 8,000 pixels across. That's the most advanced in the world. California Academy of Sciences is our nearby one with the Morrison Planetarium, and we're also working with the Hayden Planetarium in New York. They're going to have a show starting this November that'll be the first dome show that's really about modern cosmology. I'm the director of the High Performance Astrocomputing Center at the University of California, and HIPAC supports these various programs I mentioned. The summer school this summer is going to be here at Santa Cruz and Star and Planet Formation. The Galaxy Workshop, the Ra project are all supported by HIPAC. And then we also have conferences and schools at many other campuses at the University of California. Now, zspace, a Silicon Valley startup, gave us their technology, and we've created a three-dimensional visualization lab, which is in the astronomy environment. And so what zspace lets you do is you actually see, you wear special goggles, and it tracks your head. And you actually see, whoops, you see the object as if it's actually a three-dimensional object right in front of you. And you have this wand, and you can pick up things in the object. You can pick the whole object up, you can turn it around, you can blow it up. So this is a really beautiful way that you can interact with 3 dimensions. And in principle, this thing should also support 3-dimensional videos. So this is not like a passive screen. What you see depends on, if you look around, you actually see the back of the object. It's giving you the illusion, they call it a holographic workstation. It's giving you the illusion that you're actually seeing the whole thing in 3D right in front of you. So it's an amazing thing, and we're having a lot of fun with it. And we think it's actually going to help us understand what's going on. So these are some of the projects that we're doing right now using this, and it's not just my students in my group, but others here at UCSC. In fact, the computer science faculty came over and saw this thing, and they're going to have students in some of their classes come and help us, basically to get to work with this brand new technology. So astrophysical data is wonderful from the point of view of big data. I mean, big data is a challenge, as I'll explain, but our data is the best because it's clean. It doesn't have a lot of confounding features. And it's non-proprietary. After a little while, all the data gets released to the public. So, unlike medical data, for example, which is abundant and interesting, but has to be protected because it contains personal information, our data is not like that. And our data is mostly pretty well funded. Governments spend billions of dollars a year helping us astronomers for reasons that are, certainly not economic. And it's sexy in the sense that lots of people are really interested. So, for example, hundreds of thousands of people volunteer to help us classify galaxies. And incidentally, we've given all of our Hubble galaxies and our simulated galaxies to these people, and they're classifying them, and they've understood that we're not going to tell them which ones are simulated and which ones are real. We haven't figured out how to use the millions of classifications that we're getting from the hundreds of thousands of volunteers. If you're interested, you can ask me about what the problems are. But the way they do it is basically a decision tree where they answer a question and then they get different questions. So they don't answer the same questions about every galaxy, and that's one of the reasons it becomes hard to analyze. One of my colleagues here at Santa Cruz, Greg Laughlin, has this project where all the data that's available on the extrasolar planetary systems, the thousands of systems we now know about with planets around other stars, and they can try to figure out from the raw data what the pattern is, how many planets there are and what their orbits are and so on. And of course, you've probably heard about SETI at home, where people loan their unused computer time for analyzing data from the Search for Extraterrestrial Intelligence. So, and these are just a few examples of the so-called public science projects that support astronomy. Now, astronomy has a very rapidly growing amount of data. So the Sloan Digital Sky Survey produced 2.5 terapixels of images. It's basically a map of the northern sky, and a digital map. And that turned into 40 terabytes of raw data, 120 terabytes of processed data, and 35 terabytes of catalogs. And of course, you all know what a terabyte is, 1,000 gigabytes. Well, that's not a huge amount of data, but that was 2008. Currently, the archive at Space Telescope Science Institute, named after Barbara Mikulski, the senator from Maryland, who's also the chair of the Science Committee of the Senate. So that's why she's been providing lots of money for them, so they named this after her. So it's 185 terabytes of images. There's 25 terabytes of new images coming out every year. And the number of images that people take out is 100 terabytes per year. There are now more papers based on the archive data from Space Telescope than on new data. Last year is when the archive beat the new. The Large Synoptic Survey Telescope is being built in Chile right now. It is going to collect 15 terabytes per night for 10 years. Its image archive is going to be 100 petabytes. A petabyte is 1,000 terabytes, 1,000,000 gigabytes. Its final database catalog will be 20 petabytes. Today, using all the telescopes available, we find a few hundred new supernovae every year. The Large Synoptic Survey Telescope is going to take a snapshot of the entire southern sky every 2 nights. It is going to find 1,000 new supernovae every night. In about 10 years, the square kilometer array is going to come fully into operation. There are advanced projects in both Western Australia and Southern Africa. In Africa, it's called the Meerkat Project, and in Australia, it's called ASCAP. And when the thing finally goes into operation, it's going to generate, this is the ultimate, at least that we've conceived so far, survey of the H1, the neutral hydrogen 21 centimeter line. It's 21 centimeters at redshift 0. At redshift 10, it would be, at redshift 9, it would be 21 centimeters times 10, so 210 centimeters. And that's what this array is going to be looking at. And the area of the radio telescopes, the combined area, is going to be a square kilometer. That's what it's called, the square kilometer array. It will be spread out over thousands of kilometers, millions of square kilometers. And it's going to generate an exabyte a day of data. That is the entire content of the internet today, of new material in the internet. It's going to require over 100 petaflops of processing power. That's more than the fastest supercomputer in the world today. But with Moore's law, etc., we have 10 years to keep it up. The budget for this project is only about $1 billion. They'll be processing an exabyte of data. They'll be archiving an exabyte of processed data every year. So an exabyte is 1,000 petabytes. A petabyte is 1,000 terabytes. So this is 1 trillion gigabytes. To give you some sense. Okay, so that's what's going on with data. This is big data. We push the envelope, we as commoners. Now the other thing that's happening is that the architecture of the computers has changed drastically. It used to be that we wrote code for individual processors. We spread it over multiple processors using a simple protocol that basically just lets them share data. And the main thing that gave us increased power was the fact that the clocks were running faster and faster. That stopped about 2004. It's basically plateaued since then. There are several reasons for this, the biggest one of which is that the faster you run the chips, the more energy they take. And energy is expensive. Currently, 2 or 3% of the entire electric capacity in the United States is going into running these data centers. And it's beginning to have a serious impact. In fact, you probably know that the data centers are located where electricity is cheap, like on the Columbia River near the Grand Coulee Dam. Or the Department of Energy's biggest supercomputer is at Oak Ridge National Laboratory, where they've got cheap power from the Tennessee Valley Authority. So the response has been to put lots of processors, cores we call them, in a single chip. And to put several chips addressing the same memory. And also to use what we call accelerators, like graphic processor units, that can do certain calculations enormously faster. It's the equivalent of having thousands of cores in one small, inexpensive gadget. These have become very inexpensive because the gamers love these things. The huge market of millions of mostly teenage boys and adult boys who like to play fancy computer games. So this has been great because it makes the technology very cheap for us. The problem is that these things are really hard to program. There's no compilers where you can just write some high-level language like C, and it will generate efficient code that will run on these complicated computers. So we need to have computational scientists and engineers and new compilers that generate code for nodes that have cores plus accelerators, and that also, as the computer is running, doesn't allow one part to finish while another part is still grinding away, because the part that's finished is just going to sit there. That's called latency. And it's very inefficient. What you want is for the computer to constantly check and spread the work evenly so that you don't have to have large parts of your system waiting for some other part to finish. And this doesn't exist now. Another problem is that once we go to millions of cores for computation, and we're very close to that now, we're going to lose cores during the computation. So the results have to be tolerant of these faults, of these failures. So there's exponential growth in computing power, that's Moore's law, and then detectors, because we get these bigger and bigger and better detectors. And the data storage cost is falling much faster than Moore's law. And that's enabled vast increases in ambitious surveys with massive storage for archives and also simulation realism. We now can do better and better simulations, which is a good thing because until we made them reasonably realistic in the last couple of years, we weren't getting results that look like real galaxies. Astronomy is becoming dominated by these big surveys and simulations. The days when an individual goes out and looks through a telescope, I mean, people still do that, but that's not what's producing most of the important new knowledge. So how do we understand such huge amounts of data? We need new ways to examine the data in detail and also to see the broad features. And we can't archive all the data, we have to analyze a lot of the data as the supercomputers run. So over the last several weeks, we've been busy analyzing the data coming out of the Bolshoy clock simulation as the data ran, because we were told we couldn't keep it on the disk. We were using too much disk space, hundreds of terabytes of disk space, at NASA's big supercomputer center at Mountain View, California. We also have a problem that we can't move this big data. Number one, a petabyte of data would take a month to move at the current highest speed available on the internet, the high-speed internet, 10 gigabits per second. And anyway, where can we move it? There aren't very many places that can handle that much data. So in the future, more and more, we're going to have to analyze the data remotely. We're going to have to interact with the data sitting elsewhere. We'll have to send algorithms to where the data is and get back answers, including visualizations. Now, Google has pioneered this. Google never gives you their raw data. You couldn't do anything with it if they did. They give you answers, and ultimately, that's what you want. But we have to learn how to deal with that. So to summarize, we have big data, too large to move, from more powerful observations, larger computer outputs, and falling storage costs. We have changing high-performance architecture. High performance is another name for supercomputers. From network single processors to multi-core and graphic processor units. These challenge and other kinds of new things. Intel has responded to NVIDIA's graphic processor units with its mic chips. And so we have to learn how to program those. These challenges demand new collaborations between scientists and computer scientists to develop tools and scientific programmers to convert legacy code and write new code sufficient on multi-core GPU architectures, including fault tolerance and automatic load balancing. New ways to visualize and analyze big data remotely, train new generations of scientific computer users, improve education and outreach. And HIPAC, the University of California's system-wide astrocomputing group, is proposing a scientific computing institute in Silicon Valley to work on these issues. And we're trying to get Google and other big players to collaborate. I gave the keynote talk a couple of weeks ago at one of the big meetings of the computer professionals. And they seemed very interested, I must say. So, end of talk. I think I stayed within the time limit. We'll have time for some questions. And these will, of course, go up on the web. So, all of the visualizations I showed you are available on one or another of these websites. Eric Maciel, who's been doing the videoing, is also our webmaster, so he can answer more questions about exactly where to find this stuff. My wife and I have written two popular books, The View from the Center of the Universe, and more recently, The New Universe and Human Future. And the best website is newuniverse.org. This book just came out in Spanish in Spain in May, and so there it is in Spanish. This book's out in half a dozen foreign translations. Eric actually created the Spanish website. So all the same material that's here, which includes essentially all the videos I showed you, plus 2 dozen more videos that I didn't show. It's all here too. So if you have Spanish friends, tell them about it. Okay, that's it. So any questions? Yes.
How far are you from getting a cosmological prediction about planet formation?
Cosmological predictions about planet formation. Forget the cosmological. The issue is really to understand planets just in our own galaxy. Those are the ones we're going to find out about anywhere, anytime near the present. So 20 years ago, one of the world's great experts on planet formation, my colleague here at Santa Cruz, Doug Lynn, wrote an article about what we should expect in extrasolar planets. And he basically predicted that they'd all look more or less like the Milky Way, with rocky planets on circular orbits in the inner part, and gas giants on the outer part, all going more or less circular orbits. We have one example. Naturally, the extrapolation was they all look like that. Doug did point out that it was also quite possible that you could have a massive Jupiter-like planet that formed far out, and that got pushed in by the gravity of the disk outside. It's further away from the star. So he did predict that that was a possibility. Well, now we have data on thousands of extrasolar planetary systems. Most of the data that's reliable has come from the reflex motion of the star. As a big planet goes around the star, they actually go around the neutral center of mass, and the star we see go back and forth along the line of sight. And we can measure the Doppler very accurately. Steve O here at UCS, he showed how to do that, and his technology is the one that's used all over the world. I want you to appreciate that Santa Cruz is one of the main centers in the world for this stuff. And so we have data now on thousands of extrasolar, a few thousand extrasolar planetary systems. We have never found one that looks like ours. If you make a plot of the ellipticity of the orbit versus the distance, up close to the star, you've got these hot Jupiters, you've got smaller objects, there are nice circular orbits for reasons that we understand because the gravitational interaction of the star with circular orbits. But as soon as you get out to 1 AU, the distance of the Earth from the Sun, there's hardly anything that's circular. They're mostly highly elliptical, and beyond that, they're quite elliptical, which would be very hard for life to form. So you probably read that there's a certain number of planets mostly found by transit, by the Kepler project, a satellite that sadly lost its second reaction wheel and no longer is usable. And those are close-in planets orbiting dwarf stars, and they are on circular orbits. They might be a bit hospitable for life. Those stars are extremely long-lived. They'll live 1 trillion years, unlike the Sun, which has a total lifetime of about 10 billion years. But those little dwarf stars are pretty unstable. They tend to have outbursts, so that may not be so good for life. As I mentioned, we're having a big school here this summer where the leaders in the world in computational astrophysics on stars and planet formation are coming, and there's about 40-some students, half of them from outside the United States, advanced graduate students and postdocs. And it's all going to be about star and planet formation. Of course, you have to do planets and stars together. It's going to happen starting a week after the end of this program. And it's a big, big project. I mean, this is a tremendously important area because now we're getting all this data, and we do not understand it. So it's a huge challenge to understand why the planetary systems look the way they do, and I don't think anybody really understands it yet. A big frontier in astrophysics. So you ask how long it's going to be before we understand it. Who knows? 10 years, maybe, if we're lucky. Well, we are getting some insights. Mark Krummel's a faculty member here, who's the director of the school this summer, showed a couple of years ago why it is that giant stars, the ones that weigh 50 or more times the mass of the Sun, form in pairs and almost always with the other star being about the same mass. He ran high-quality simulations, and they always produce that, and he understands why that happens. So you know, there's pieces of progress, but lots we still don't understand. Andrew?
I'm guessing the question was also about like a resolution question. Like you mentioned that you can simulate the whole observable universe at low resolution. What would it take to be able to have a cosmological simulation in which, at least in one small area, you can zoom in and actually can say something on the scale of planets?
Well, you wouldn't need to do a cosmological simulation. Why would you want to do that? I mean, it's hard enough to simulate a galaxy. No one today could begin to simulate a galaxy and also stars with planets.
Sure.
Because, to simulate I told you that our really high-quality simulations, the ones that my group is doing, have a resolution of about 100 light years. To simulate the evolution of the gas cloud that forms a star, you've got to have a resolution that's better than 1,000th of a light year. Because remember, it takes about 1,000th of a light year, less than a light day, for the light to cross the solar system. So the problem is that simulations have limited dynamic range. That's the ratio of the whole scale of the simulation divided by the smallest scale. And right now, the best you can do is about 10 to the 5, maybe if you really push it, 10 to the 6. Maybe when we have quantum computers, we'll be able to have a big jump, or we can do simulations. Right now, it's been sort of slowly growing with the scale factor that this ratio that we can simulate. So NASA Ames, together with Google, just bought one of these new D-Wave quantum computer systems with something like 10 qubits. And I got an email, because I'm one of the big users, saying, what Would you like to use it? What can we do with it? So I'm going to have to study quantum computing now, because it looks like it's going to start coming online. 10 qubits isn't much, but if they can do 10 qubits, well, 20, 30, you're talking about real computing. That's enough to make the banking industry very nervous. Right. But it also might be enough for us to be able to solve problems we couldn't solve before. And certainly for young people, I mean, the frontiers, I mean, you know, I tried to give you a sense of what the issues are, but we don't really see any horizons. As far as we can tell, computing is just going to get better and better. And the data is going to get better. And we can start to really understand how galaxies form and how stars form within galaxies and how planets form around stars. And maybe even begin to get a sense of how likely it is that we can find other Earths. I mean, we haven't found any yet, so there must be. And of course, I didn't mention it before, but the square kilometer array is 10,000 times better than any radio telescope that we've ever had. So the search for SETI will be an entirely new project with square kilometer array, the search for extraterrestrial intelligence. So we'll be able to get radio signals from a much larger region, thousands of times the number of potential sources that we've had up until now. So who knows? I mean, you know, the great thing about astronomy for the last 3 decades, and as far as we can see into the future, is new windows keep opening.